Welcome to the AP Physics lecture. This is on dynamics. We're talking about law of motion. Here we're going to be talking about drag. Drag in simplest terms, we know that friction slows an object down to its molecular collision that occurs on the surface. If you think about a fluid, in mostly gases or liquids, you're going to be talking about this idea of drag now. Drag uses the letter D, and it can be thought as the friction of a fluid. Again, because there's still molecular interaction between an object and the air or water. Okay. Here's the formula. Please understand, you're not responsible to memorize the equation, but what you need to understand here is that the drag force, D, is equal to, ignore this part, ignore this part, ignore this part, right here, velocity. So this depends on the velocity, right? But you see how it's squared? Velocity squared. So if you ever double the speed, so let me show you, D is equal to, ignore the other stuff, right? Stuff here, V squared. If you take out the V and you double it, so let's say it becomes 2V, and then you distribute, D becomes what? 2 squared becomes 4. V becomes V squared, right? So what happens to the drag? It quadruples. That's where the 4 comes from. So the faster an object goes, the more air resistance it has. And it has a lot because it is quadrupled. Here is a vector analysis of the drag. Imagine an object falling. When an object falls, we saw that force of gravity is always pulling it down. So here, the gravity is pulling it down right here. So gravity is the only thing pushing it down. Then a few seconds later, you have a little bit drag. So now you have a bit of drag. Okay, this is at the start. This is like a few seconds later. Okay. You would have something like this. Then after, you're never going to have to solve for the t, but let's say after a couple of seconds, like 10, 20 seconds, right? 20 seconds or so, right? Roughly. So I can just say roughly 20 seconds, right? It should be balanced out. Now the drag is equal to the force of gravity. That is the definition of terminal velocity, when drag is equal to the force of gravity, okay, or your weight. Terminal velocity is when the object is at equilibrium because the drag force is balanced off by the force of gravity. So A equals to 0. This is when the skydivers, like people who jump out of planes, when they start doing the crazy move, is after they they're in terminal velocity. Okay, so if we looked at this example here, a person, a 90 kilogram person, their weight is 882 newtons, right? If they jump off the airplane here, they just jump, right? They have no drag at the start. So right now, their force of gravity is pulling them down at negative 882 newtons. Their acceleration is negative 9.8. This makes sense because the acceleration is pulling it down. Now there's a bit drag left, right? So let's say this is 1 second later. Okay, now the force drag is 300 newtons. Ignore how we got the calculation, right? So the acceleration starts to decrease. Then a couple seconds later, so let's say roughly 3 seconds, it's 600 newtons, right? The drag. So the acceleration decreases. Then here, let's say this is roughly 7 seconds. You're not responsible for the time calculation, okay? You see that it's 882 newtons up, which is balanced out with the force of gravity, which is going down. Notice that during this whole process, acceleration is going towards 0 meters per second squared. Why? Because the friction force here is opposed to it. Okay? So drag in this process, in this whole process, is going towards the value of Fg. As drag becomes Fg in this situation, acceleration becomes 0 because they balance each other out. That's the idea of terminal velocity. Okay, this is looking at it in a vectors. Now we're going to look at it in a graph to give you better visual understanding. After depressing the acceleration, the speed of a car begins to increase. Okay, so ignore the car scenario. I'm gonna just think about this in terms of the person falling. So here the person starts to fall, right? And the person's the person's velocity is super strong, right? They're just falling. Now you have a little bit of the drag, okay? Because air resistance increased, right? Okay? Because your velocity keeps increasing because of the acceleration, you're going to have more drag, right? More velocity, but there's more drag, right? You keep going, but your drag is increasing. The red line here is due to drag. So the drag is what's preventing this. So normally it, let me change this to red. Normally it should look something like this, right? So it should look something like this. All right. Okay. This, if it's constant, right? Acceleration. Okay. But the curve here, the acceleration here, remember, this is the slope of the velocity time graph is the acceleration, right? So here, this is the acceleration. This is strong acceleration, right? So this is like A, okay? Then here, the acceleration is smaller. Then the acceleration here is super small. Then the acceleration is super small. Why? Because the drag is decreasing the acceleration. Because the faster the object, more drag. We talked about that. So as speed increases, it's going to be equal to the terminal velocity. That terminal velocity is the horizontal asymptote. You need to understand an important claim about drag. It is initially at 0 here, but as it increases, it goes to this point, which is the maximum. This is when terminal velocity is equal to mg, or sorry, not terminal velocity equals to mg. The force of terminal velocity is when the force of drag, so we can use the letter D, is equal to force of gravity, mg. Now, I want to compare a couple of things between friction and drag. Friction talks about the surface of an object. The rougher is greater friction. How hard a surface pushes against another, right? It does not depend on the surface area. And it depends on the object if it's moving or standing, but it's not its speed. Okay, kinetic, mu, or mu static. But for drag, it depends on the density of the fluid. Okay, that is rough. Density refers to how packed the molecules are. It depends on the surface area. How many molecules are you hitting at that time, and the object speed. Okay. This technically is like the math for fluids and air, while this is the math for solids. Motion. For friction, it is both standing, which is static friction, moving is kinetic friction. But drag, the object has to be moving. There is no drag when the object is stationary. Why? If you're not moving, air isn't really hitting you. Vague answer, right? Because even if you're standing still, air can still hit you, right? But drag is a result of you going against that. Here's the value. Okay. The type of motion describes the formula and coefficient needs to determine the force of friction and drag. Drag depends on the speed of the object. Drag increases with speed following a set function for the fluid. Okay. This is just a summarization of the concepts that you should remember when you look at drag and friction. There you go.